Welcome back, students, to our Chemistry 1510 video notes. In this section, we're going to be talking about valence electrons. So when we talk about valence electrons are the outer electrons. And these electrons are important because they are what are involved in bonding. So when we talk about the outer electrons, we mean the electrons that are furthest away from the nucleus. So in this picture here, I have my nucleus here in the center consisting of protons and neutrons. Then this is a Bohr model of an atom, so I have energy level 1 here that has 2 electrons, and I have energy level 2 here. So in this case, I have 1 electron in my energy level 2, and this would be my valence electron. There's only 1 valence electron in this example. The electrons in energy level 1 in this example would be the core electrons. These electrons are not involved in bonding. Whereas the valence electrons are. So this is how you would pictorially figure out your valence electrons. Let's use an electron configuration to figure out our valence electrons. So here's some examples. When I look at oxygen, I can write its electron configuration, and I notice that I have 2 subshells that are in the second energy level. So all of the electrons in energy level 2 are going to be valence for oxygen. Because remember, what we're searching for is the electrons that are furthest away from the nucleus. The electrons that are furthest away from the nucleus, in this case, are in energy level 2. Then those electrons are subdivided into the s orbital and the p orbitals, but they're still in energy level 2, so they count as valence. The same idea is going to hold here for sulfur. These ones in bold in energy level 3 are going to be your valence electrons. It gets a little bit harder once you start having d orbitals. And it's not really harder. It's just that you have to recognize that the definition of valence are the electrons that are the outermost. So they're the furthest away. So if we look at our little Bohr diagram, if that's my nucleus and this is energy level 1, 2, 3, and 4, here in energy level 4, this is further away from the nucleus. It just so happens that energy level 3, which contains a 3d orbital, fills before the 4p because that's the filling order that it goes in. But distance-wise, it's closer to the nucleus. So the d orbitals are never going to be valence electrons. So here, again, the same idea is that the electrons that are in the outermost layer are valence, and that's going to be the electrons in the 4s and the 4p. Same idea here, the d electrons are not counting. They are in an earlier energy level. So if you have energy level 5, these are going to be your valence electrons. So you would just add up the electrons that are in the s and the p orbitals. If you had something simpler, like if you had something like lithium, you'd have 1s2, 2s1. This would be your outermost shell of electrons, and so your 1 electron in the 2s1 would be your valence electron. So notice how oxygen has a total of 6 valence, sulfur has 6 valence, selenium, has 6 valence, tellurium has 6 valence. And so when we come down to this periodic table here, if you look at a periodic table where the letter abbreviations are written in, you are going to notice that oxygen, sulfur, selenium, and tellurium are all in the same column. So when elements are in the same column, they have the same number of valence electrons. And it's really convenient that we can just essentially count from left to right on the periodic table the number of valence electrons. So everything in column 1 has 1 valence electron. Everything in column 2 has 2 valence electrons. We commonly ignore the D block here because the D block contains transition metals, which sometimes do some unusual things. So then we come over to column where aluminum is 3 valence electrons, 4, 5, 6, 7, and 8. So we can just count our columns ignoring the D block, and that's going to be a quick and easy way to figure out your number of valence electrons.